Okay, so the Middle Permian extinction then is perhaps lesser known to many of you than its famous sibling, the End Permian extinction. But I want to just talk through some work that myself and quite a big team of us named there, some of which are in the audience today, have been doing over the last few years in Spitzbergen. But first of all, I really need to introduce this extinction event to those of you that aren't really familiar with it. So we've seen a few diversity curves already today. This is one modified from Bambach in 2004. And you can see we've got genus extinction magnitude on the left there and time along the bottom from the Cambrian to the present day, left to right. And the End Permian, of course, the greatest extinction in Earth's history, stands out like a sore thumb there, but we don't have to go back too far to find the Guadalupian or the Capitanian, as it's otherwise known, or the Middle Permian mass extinction. So depending which version of the geologic timescale you use, we're looking at an event 7, 8, 9 million years before the End Permian catastrophe. So just to very quickly summarize the casualties of this extinction, it's known from the marine sphere mainly, but there are also losses on land as well. So if I start down at the bottom there, we've got plants and Dinocephalian tetrapods. So the Dinocephalians, terrible heads, the main vertebrates on land at this time, they suffer 100% extinction. So we're seeing losses in the ocean as well as on land. The principal group in the oceans that suffer are the fusellinid forams. So this is where the extinction was first recognized in the record of forams from southwest China. The famous paper of Stanley and Yang from 1994 was when this extinction was first really discovered. So we're talking the last 20 years or so of research effort has produced this kind of data. So death and destruction in southwest China then, so we were responsible for some fieldwork and papers from 2007 to 2009. And southwest China is a fantastic place to examine this mass extinction because we have the record of extinction in these fusellinid limestones, also packed with calcareous algae. But we also have the evidence of yet another large igneous province that we think is responsible for a mass extinction. So this is the Meishan large igneous province of southwest China. And the extinction there happens precisely at the onset of volcanism. And then when we get limestones returning a bit later on, we lack all of these Middle Permian fauna and flora. So we have death by volcanism in southwest China. If you can make this out, we also have a very large negative carbon isotope excursion in China. Now, this hasn't really been reproduced in other parts of the world, but we have a -6 excursion in the carbon isotope curve, which we assume is linked to the input of light carbon dioxide from Meishan volcanism. Now we can use that as a geochemical clock, a bit of wiggle matching, and try and reproduce this curve in other parts of the world to try and see if we have a global mass extinction. So that's one of the definitions, right? For a mass extinction, it has to be a global event. So that brings me on to the Permian faunal provinces here. And what we're really testing is if volcanism then in China or in eastern Tethys, these are really based on brachiopods, these provinces, and forams, but whether volcanism there can cause a mass extinction in the Boreal realm of northern high latitudes, which brings me on to Spitzbergen fieldwork. So we spent 2011, 2012, 2013 working in Spitzbergen. The Permian is coloured in green there, and I'll just talk through some data from several sections. So this is the famous Festningen section, which is the type section for the Kapster-Rostin formation, which is the middle to late Permian formation in Spitzbergen. Van Quelenhammer a bit further to the south, and also a section a little offshore on a small island called Iholmen. So I'll really just take you through the fossil record of these sections and show you that we do indeed have a boreal mass extinction. So Festningen then, as I say, it's the type section for the 400-metre thick Kapster-Rostin formation. We have repeated cycles of pale cherts, fossiliferous yellow limestones, and dark cherts. And actually, one of the key things here is that the very rich brachiopod and bryozoan fauna is present in all three of these lithologies. So it's there throughout, which is key, really, if we're trying to tease apart things like biases in the fossil record. We have fantastic bryozoan and brachiopod faunas, also numerous bivalves. And this is a cool water setting. This is facing the Paleoarctic, even though we're only 45, 50 degrees north. This is a cool water a ramp setting but absolutely packed with bryozoans and brachiopods, which give us plenty of evidence to study in terms of looking for a mass extinction. So we have brachiopods. This is just a few of the fauna that I've photographed. So we have brachiopods on the left, bivalves on the right. But just to summarize those into a composite range chart of the various sections that I talked through, we have about the top 100 meters, or we have the top 200 or so meters of the Catastrophic formation here, and you can hopefully see each one of these little black dots is the presence of a species or genus of brachiopods with a handful of bivalves thrown in. And what we see here is about 40 meters from the top of the Catastrophic formation, we have an extinction level. So we lose 87% of the brachiopods at this single event bed here. And then, a little bit higher up, we get some radiations. So about 20 meters later, we have radiations, especially amongst the bivalves, particularly the pectinid bivalves. They start to appear here. So this is rather like the transition that has been noted by several authors in recent years from the kind of Paleozoic brachiopod-dominated benthos to a more Mesozoic-dominated, or benthos dominated by bivalves. And this is the sort of thing that we're seeing here still within the upper Permian strata. About 10 meters from the top of the section, we get our last Permian body fossils. So those bivalves and the remaining brachiopods disappear at this level. Maybe this is, I've seen suggestions of a diachronous end Permian mass extinction. We're still about 15 meters below the PT boundary at this level. But these are our last Permian body fossils. The only thing we have left after this are zoophycos trace fossils, which is slightly odd because this is suggesting that we don't have anoxia developed at this level. We still have a benthos giving us our zoophycos trace fossils. But that's all that's left above this 10 meter from the top of the Capstorosten level. So, okay, we have a boreal mass extinction, but let's look at the interesting stuff then, the timing and the cause. So we still need to really tie this event in to the event in southwest China and other parts of the world. And as I mentioned, we try and do this with geochemical clocks on the basis of things like carbon isotopes. So firstly, we do see a negative carbon isotope excursion. On the left there is the Festningen section. Those are 3 separately produced carbon isotope curves, all in very good accordance with each other. But our shift here is only about 2 per mil, so it's not on the same magnitude as we see in southwest China, which may be slightly problematic, but it's certainly a similar pattern, just not the same level of magnitude. We also have quite abundant trace metal data, so these are redox-sensitive trace metals, uranium, molybdenum, and vanadium, and these are all enriched, even when normalized against aluminium, these are all enriched around about the extinction level at Festningen. So this is actually telling us that we have perhaps some evidence for anoxia developing at this level, which is interesting because anoxia isn't implicated in the mass extinction in other parts of the world, such as China and Japan, where it clearly develops significantly after this extinction level. So maybe this is a local signal in Spitzbergen. And that signal is confirmed by the presence of my favorite things, which are pyrite framboids. I love spending time on the SEM, listening to music and counting these bugs. Well, they're not bugs, they're lumps of pyrite. But we have tiny framboids which are indicative of the development of anoxia. So we see lots of these really small pyrite framboids forming around the extinction level. So we clearly have some, at least localized anoxia here. But as I said, that carbon isotope record isn't really strong enough for us to be able to say, yes, this event is exactly the same level as the extinction level in southwest China, which is a bit of a shame. So we need to try and strengthen the age model. So we did that with strontium isotopes. The brachiopods are incredibly pristine, so that we screen them with cathodoluminescence to check that they weren't altered. Once we've got them out of the Catastrophic formation, which is just about the hardest rock on the planet. And then we were able to analyze them for their strontium isotope ratios. This is the global strontium curve from Permian seawater from Court et al. 2006. And what we see in the global curve is that the Capitanian is pretty much the nadir in the strontium isotope record. It's the lowest point in the whole of the Phanerozoic, pretty much. And there's an inflection point there down at the bottom where the ratio reaches its lowest ebb and then starts to rise again, presumably as a result in increased terrestrial runoff from land. There's supposedly a wetting of climate around about the GL boundary, so it gets quite arid for a prolonged period, and that's also seen in the terrestrial floras of China. We see this aridification driving this ratio down, and then it rebounds as the climate starts to get wetter again in the late Permian. But the key thing is, we also see this inflection point in our brachiopods from Capster Austin, or Festningen. So we see this rebound, we see the strontium curve declining, and then we get these much more, these increased values up in the upper part of our section. And if I was to draw a line on our section as where the extinction level is, it's round about there. It's precisely at the inflection point of the strontium isotope curve. So we have some kind of tentative evidence, confirming our tentative evidence from carbon isotopes, that we have our extinction falling somewhere in the mid to late Capitanian. Now, I'd love to get more data, which is what I am doing, to really try and pin this down. It's also in accordance with the published magnetostratigraphic evidence from Svalbard as well. So we think this is a mid to late Capitanian extinction, which is the age of this extinction event in southwest China. So that's good. What about the wider boreal realm? So this is Vegenhalvö in Greenland, in eastern Greenland, which is situated maybe up to about 1,000 kilometres away, but effectively very, very similar stratigraphy, and also showing as a Paleoarctic realm. And Sverdrup Basin, which Steve Grasby and colleagues have worked on extensively in northern Canada, the records from Greenland and Sverdrup show very similar losses, probably of a similar age. So if we look at the refined Greenland conodont biostratigraphy, we see that there's a similar turnover in brachiopods, and although people will argue about it because the conodont biostratigraphy is being disputed, they seem to be of a similar age, and the same thing happens in the Sverdrup as well. We see also in East Greenland a very familiar late Permian short-lived recovery. There's little evidence for widespread anoxia in these sections, at least not until a long time after the extinction, which would be associated with the Permian-Triassic boundary anoxia. So there does seem to be just a localized signal in one of our Spitzbergen sections for anoxia. But what is interesting, and I think key perhaps in this extinction scenario, is that there's the widespread loss of carbonates in the region. So above the extinction level in Spitzbergen, there are no more carbonates. There's none in the upper Permian of Sverdrup, and there's none above the Vegenhalvö formation in Greenland. So this is quite interesting. This is perhaps indicating a death by acidification, which is now being more widely implicated in several other mass extinction scenarios. So to summarise, what we see then in Spitzbergen is an abrupt extinction, accounting for 87% of the brachiopods. I think we can now tentatively correlate this with the Tethyan extinction horizon, which means that we do now have a global mass extinction. We can say that this is a significant, or an abrupt and a widespread extinction event, which suggests that I would say that this extinction event deserves to be included in the Big Five. So we should now call it the Big Six, or if you consider the modern day losses, mass extinction in the weighting, we could call this the Big Seven, perhaps. So I think this one really does now deserve to be included in that exclusive club. One of the things I am interested in testing is latitudinal bias to extinction. So do the polar regions and the cool water regions suffer more or less in past mass extinctions than the tropical regions? In this event, in fact, if you look at the brachiopod extinction magnitudes in South China, they are also 87%. So we have a very similar magnitudes of extinction in the high latitudes and the low latitudes. So actually in this event, I think perhaps there is no latitudinal bias, which would suggest there's no role for warming or cooling. There's no advantage for living or being cold water tolerant or a warm water species in this extinction event. So anoxia plays a role at least locally, less so globally. So I don't put anoxia down as the principal cause of this extinction event. And as I've mentioned, we have the total loss of carbonates in the Paleoarctic regions. So this is consistent with acidification as a cause of this event. But I think, just to go back, I think we're perhaps looking at different extinction mechanisms in different places. So the polar regions being cooler are more susceptible to acidification because cold water can absorb more carbon dioxide, which is the driver of acidification. So we don't see the total loss of carbonates in tropical regions. In fact, they bounce back quite quickly above the volcanic pile of the Shan. They've just got a totally different fauna and flora in them. So maybe we're looking at different competing extinction mechanisms in different parts of the world. But what we can say is that the role of Shan volcanism in this extinction scenario is strengthened if we have this temporal link in China, which looks pretty strong. If we can now link this event, say it's of a similar age, if not the same age to the Chinese sections, then we strengthen the role of Shan volcanism. But I'd be the first to admit that, as with all mass extinctions, the key now is to refine the age models and really tie these things together. So some high-resolution geochronology would be fantastic on these sections. So that's it from me. Just to say thanks to the funding bodies, the Norwegian Polar Institute, Marie Curie Actions, and the Natural Environment Research Council, and some people that aren't named on this paper but took part in fieldwork and have been very supportive of this project are all pictured and listed there. Okay, thank you.